Okay, so what I want to move on to now is following this same idea that we've just established, which is that when we multiply by a complex number, we stretch the entire complex plane by the modulus of that number we're multiplying by, and we rotate by the argument of that complex number we're multiplying by. So what if we wanted to take a complex number, let's say z, and we wanted to raise it to different powers? Okay, so this is kind of where I'm aiming for. I want to come up with a systematic way of taking a complex number, which I've just written as z, so that's like x plus iy, or whatever you need, and raising it to just different powers, so power of 2, power of 3, power of 4, etc, etc. Now, in order to do this, because we've established that there's a stretch and a rotation, and we're talking in terms of the modulus and the argument, we need to make sure that we are working not in Cartesian form, but in a modulus argument form, so either Euler form or polar form, right? Let's do it with an example. So let's consider z is equal to 3 plus 4i. Okay, so I'm just going to consider this one here, 3 plus 4i. And then literally what I'm going to do, in fact, let me stop that there. Okay, literally what I'm going to do is raise it to different powers. So I want to consider what would z to the power of 3 be equal to. So that's what I want to find. So in order to do this, because I know that when I multiply by a complex number, I have that stretch and I have that rotation, I need to convert this into modulus argument form. Okay, so can you spend maybe a minute or so just converting that into modulus argument form for me? In fact, I'm going to change my mind. Because these numbers are a little bit awkward, I'm just going to go with 1 plus i. It just comes out a bit nicer. I mean, you can do it with 3 plus 4i, but the numbers come out a bit nicer if we do 1 plus i instead. So yeah, 1 plus i, what happens if I raise it to the power of 3? So let's first, we'll convert it into modulus argument form. So z is just going to be root 2 times by the cosine of pi by 4 plus I times the sine of pi by 4. Of course, we could have also put it into Euler form as well. I'm going to work with it in polar form for the time being, and then hopefully you can establish how we can get Euler form and how it relates. Okay. Right, so we want z to the power of 3. Now, in order to do this, we just need to think about the two operations which happen when we multiply by complex numbers. Because of course z cubed is a bit like z multiplied by itself 3 times. Yeah? So z cubed is literally z times z times z. So what happens when we multiply by a complex number? What are the two operations? Stretch by
modulus.
The modulus, good.
And rotate
By?
its argument.
By argument, perfect. So you stretch by its modulus and you rotate by its argument. So if I think about this, okay, this is my complex number at the moment. So if I just write down root 2 times by the cosine of pi by 4 plus I sine of pi by 4, let's see if I can establish what z cubed is going to be equal to. So this is z at the moment. I want to figure out what would happen if I take z and I cube it. Okay. First things first, I'm going to take the modulus, because at the moment what I'm saying is that my complex number is a distance of root 2 away from the origin. That makes sense? So when I multiply by z, let's just multiply by z first of all, then we'll do multiply by z again. Are you happy that I'm going to take that distance and I'm going to stretch it by another root 2? Yeah, so I've taken root 2, that distance, and I've made it root 2 further along. So how far away from the origin am I at the moment?
2.
Good, because I've taken root 2 and times it by another root 2. So if I times it by root 2 again, where am I going to end up at?
2 root 2.
2 root 2, perfect. So literally I've just taken this modulus and I've just times it by itself 3 times. That make sense?
Yeah.
Yeah? Now let's think about the rotation. So we're going to deal with the argument. At the moment, I'm pi by 4. So if you imagine my arm is like my complex number. At the moment, I'm pi by 4. if I rotate by z once, you're happy I'm going to rotate by another pi by 4.
Yeah.
And if I rotate by z again, I'm going to go another pi by 4.
Yeah.
So in total, what I've done is I've taken pi by 4, and I've gone pi by 4, then another pi by 4, then another pi by 4. In other words, I've gone 3 pi by 4. That's nice and easy, right? So what I'm proposing is that z cubed is going to be, well, we've established root 2 to the power of 3 is 2 root 2. And then this, well, 3 times pi by 4, I can just write this 3 pi by 4, I sine 3 pi by 4. That's z cubed. Yeah? That's it. Easy as that. Now, of course, I guess, because we were given it in Cartesian form, we should probably leave this in Cartesian form as well. Okay, so can you have a go, just like we did at the start, can you have a go at converting this into Cartesian form for me? Minus 2 plus 2i. Yeah, I was kind of thinking it's just a right angle, it's just an isosceles right angle triangle, so actually it works out quite nice. Cool, excellent. Okay, so that would be z cubed. And that's the process to find a power of a complex number, okay? So powers of real numbers, they're relatively straightforward, we can do that. Powers of complex numbers, we just need to think about exactly what we established. Multiplying by a complex number means that you stretch it by its modulus and you rotate it by its argument. So because you're taking this complex number and multiplying by itself, it just means that the argument just gets rotated and the modulus just gets multiplied, okay? So what can we say in general then? Let's try and formalize this to a sort of a nice general result. So if I take a complex number, let me clear the board first. Okay, so if I take a complex number, z, and just for the sake of argument, let's assume that this is in polar form. So let's write this as r times by the cosine of theta plus I sine of theta. So if I take this complex number and I want to raise it to any power, so just raise it to the power of n, what I can say is that my modulus gets stretched by however many times I'm raising it to the power. Okay, so if it's 3, I multiply by itself 3 times. If it's 10, I multiply by itself 10 times, etc. So yeah, this is going to be, well, say 10, this is going to be n. Yeah? And then my argument, well, that just corresponds to a rotation. So if I'm rotated by theta already, I'm just going to keep rotating by theta. Hence it's going to be theta plus theta plus theta plus theta n times. Yep. So it'll just be n times by theta plus I sine of n times theta. Happy with that? Yep, that's in general. I can give you any complex number now, and I can ask you to raise it to any power, and you just use this result. Now actually, the guy that came up with this was someone called the Moivre. Hence, this idea is called de Moivre's theorem. Right? So if I say use de Moivre's theorem, I'm just literally calling that. Okay? Now, I always find complex numbers fascinating because the way which I teach complex numbers, you've seen, very geometric, and I actually have things going on the screen to be able to visualize things. The guys that came up with this originally, they couldn't visualize it, right? They didn't have access to all these sort of computational tools and things like that, which I find even more incredible, the fact that they came up with these really powerful ideas without visualizing stuff, which, you know, just shows how genius they are, I guess. But yeah, basically, that's all that's going on there. Okay. Any questions?